Alright, so hello everyone, I'm Siddharth. Okay, just one second. Is this better now? I have restarted it. Alright, so hello everyone, I'm Srishi Siddharth. I'm a PhD student associated with the Center for Systems and Control at IIT Bombay. I'm also the TA for this course, Advanced Linear Continuous Control Systems. So let's begin with second week's tutorial session. Let me know if you have any issues with my voice or my screen sharing. Alright. So let's begin. Okay, so let's recall a few concepts before looking at some questions. Right. So in the first week, we looked at two canonical forms, controllable canonical form and observable canonical form. And in the second week, we looked at canonical forms, but in the diagonal structure. So it's canonical, diagonal form, and the Jordan normal form. So to convert a straight space model or a differential equation to the diagonal form of the Jordan normal form, we require the concepts of partial fraction expansion. So this was in week 2. And in week 1, we looked at the CCF and OCF forms. Alright, so let's first begin with the partial fraction expansion of a general transfer function, and then we move on to the diagonal and the Jordan normal forms. Alright, so there are a few cases. So we'll start with the simplest case first, where you have some ratio Bs over As, example the transfer function, and it's written in the form of some constant times roots of the numerator. So it's zeros, s plus z1, s plus z2 till s plus zn. And then we have poles at p1 till pn. So this is s plus pn. And let's also assume that m is less than n. Is the number of zeros are less than the number of poles, which means it's a strictly proper transfer function. Zi's are zeros, pi are poles. So this is the simplest case. So we assume that P1, P2, Pn are all distinct. So for distinct poles, or you could also say distinct eigenvalues. Partial fraction expansion is as follows. So Fs can be written as some constant C1 over S plus P1 plus some other constant plus P2 till Cn upon S plus P. And how would you find these coefficients? So it's easy. C1 is actually Fs times S plus V1 at the value S equals minus V1. Right, so let's look at a question. So let's say that if S is S plus 3 over S plus 1, S plus 2. Okay, so first we should observe that it's a strictly proper transfer function. Transfer function. And we have distinct roots. Alright. So Fs can be written as C1 over S plus 1 plus C2 over S plus 2. This means that C1 is, as written here, it is S plus 3 over S plus 1, S plus 2 multiplied by S plus 1 and the whole expression evaluated at S equals minus 1. So please tell me what this is. I'll write down the expression for C2. S plus 2 evaluated at S equals minus 2. So you can see this cancels out, this cancels out. And what is C1? And C2 is, so it's minus 2 plus 1, which is simply minus 1. So this implies that f of s is 2 over s plus 1 minus 1 over s plus 2. You can also just cross check that us evaluating this is exactly equal to this. Alright, so now let's look at the next case. So case 2 is when m is greater than equal to n. Let's see an example. So f of s is given by s cube plus 5s square plus 9s plus 7 over s plus 1, s plus 2. So this is the case when the degree of the numerator polynomial is greater than that of the denominator polynomial. So let's just expand the denominator first. This is 9s plus 7. And this becomes s square plus 2s. This becomes 3s plus 2. Okay. So let's simplify this. S square plus 3s plus 2. Okay, so let's multiply by s first. This becomes s cube plus 3s square plus 2s. Then we have 2s square plus 7s. So multiply by 2. This is s plus 7. So I didn't write it correctly. Let me just check once. Oh, yes. So plus 4. So this is, yeah, plus 3. So therefore, f of s can be written as s plus 2 plus s plus 3 over s square plus 3s plus 2. Okay. And now this is a strictly proper transfer function. So they are simplifying the expression and using case 1 to solve f of s when m is greater than equal to 1. This is strictly proper transfer function. Okay. So now the third case is fs involves multiple poles at the same location. Multiple poles at the same location with the s. Okay, so if this is so, then let's consider an example. F of s is s square plus 2s plus 3. And then we have 3 poles at minus 1. So this is a strictly proper transfer function, but we have multiple poles at minus 1. So this is strictly proper. Then with multiple eigenvalues are s equals minus 1. Okay, so in this case, f of s can be written as c1 over s plus 1 cube plus c2 over s plus 1 squared plus c3 over s plus 1, and this should be equal to s squared plus 2s plus 3, which is f of s. Okay, so if you cross multiply by s plus 1 cube, we get c2 s plus 1 and c3 s plus 1 squared, which is equal to s squared plus 2s plus 3. Alright, so you can observe that if you put uh, s equals minus 1 on both sides, we get the value of c1. We have to get the values for c2 and c3. So you can see if we differentiate this equation, let's name it 3. This is 1. So if we differentiate 1 with respect to s and then substitute s equals minus 1, we'll get c2. So we differentiate 1 only once with respect to s to obtain c2. Of course, put the value of s equals minus 1 after differentiating. Then differentiate 1 twice with respect to s and put s equals minus 1 so to obtain c. And of course, you can also verify that you have the correct values for c1, c2, and c3 by substituting them. Yes, is there a question? Mohan Habani. If it's not, could you please mute yourself? Or okay. So let's just revise quickly the controllable canonical forms CCF and MCF. So it's controllable canonical and observable canonical, controllable and observable canonical forms. So we wrote the state matrix as a chain of integrators. Let's say it's a system with n states. Then the A matrix is given as 0, 1, 0, 12. We shift 1. And then in the last row we have minus A0. Sorry, let's make this as AN. Times the state vector plus B times U. Plus B has only one at the entry and then 0 slope. So this is the representation in the controllable canonical form of a function with this transfer function. So it's B0 s to the power n plus B1 s to the power n minus 1. So you can see that the sum of these coefficients is always n. B2 s to the power n minus 2 plus Bn over A0 s to the power n A1 s to the power n minus 1 and so on till an minus 1 x plus an. So as discussed in the last tutorial session, we begin from here. And in the standard form, we assume that a0 equals 1. Okay. Then we also have the C vector, which is Bn minus, this is the first one, so B1, E1. Let me just see. This is 20. We'll start from B0 then. So B0 an, then Bn minus B1. Just one second. Bn minus 1. And this remains B0, an minus 1. So on till this remains B0. This becomes A1 and B. This vector times x plus B0 U. Let's look at a question. So G of S is 3s cubed plus 6s squared plus 5s plus 7 over s cubed plus 6s squared plus 15s plus 11. Okay, so you can observe that this is a proper function, not strictly proper. Okay, so x dot is already given to us. It's 0, 1, 0, 0, 0, 1. And then the last row is going to be starting from here. So it's minus 11, minus 15, minus 6 times x plus 0, 0, 1 times u. And y equals the vector c, which is abc times x. Thus we're going to have b0 u, so it's going to be 3 times u. So we have to determine the values of a, b, and c. So we have already looked at the expression. So I'll wait for a few minutes and you can calculate this. So if you calculate any of these values, you can just unmute yourself and let me know. Okay, so what is the value of A? We have B3, it's 7 minus 3 divided. And B2, B is 5 minus 3 into 15. We have 6 minus 3 into 6. These are minus 26, minus 40, minus 30. Alright. So we have looked at the partial fraction expansion, and we have considered all the three cases, and we have also recalled the control building algorithm. Alright. So now let's move on to the Jordan normal form. So in the diagonal and the Jordan normal form, the objective is to write the system matrix A in terms of any of the diagonals with non-zero diagonal elements and then zeros everywhere else. So if it's the case of simple eigenvalues which are not repeating, then you have just a diagonal matrix. And if you have multiple eigenvalues, then we'll see how the matrix A changes. So this canonical form goes directly from the partial fraction expansion of the transfer function. Right. So let's look at the simplest case, which will have distinct eigenvalues. So it's case 1, diagonal canonical form for distinct eigenvalues. Okay. So the transfer function is y over r of s. Because again, that's v0 is to the power n plus v1 is to the power n minus 1 till bn. So we have n0 and then we also have n4. This plus v1 s plus v2. So the distinct eigenvalues means the eigenvalues on which the numerator are equal. And also observe that this is a proper transfer function. V0 not equal to 0. Otherwise, it would be strictly plotted. Okay. So we can rewrite this as V0 constant over S plus V1 plus V2 over S plus V2 and so on till the nth eigenvalue. That is C over S plus P. So if we rewrite this transfer function in the terms of constant C1, C2, Cn, then the A matrix that we get are just minus P1, minus P2, minus Pn. This is a diagonal matrix. So all the other elements are 0. X. In this case, the B vector is the vector containing 1 in order of matrix. Y is going to be C1, C2 till Cn. These coefficients, which needs to be calculated, x plus b0 unit. For strictly proper transfer function, this would be 0. So equal to 0. for a strictly proper transfer function. Alright, so this was the case for distinct eigenvalues. Now let's look at multiple eigenvalues. We call it the Jordan normal form, the Jordan canonical form. Multiple eigenvalues at the same location. Okay. So let's just rewrite the transfer function. What is what RS? The numerator is the same. That's B0 h to the power n, B1 h to the power n minus 1 till Bn. Okay. Now let's consider the case where we have maybe the first eigenvalue. It's repeated 3 times. So S plus P1 Q, then the rest are distinct eigenvalues. So S plus P2 till S plus Pn. So we have already looked at the partial fraction expansion of repeated poles, and we want to use that to write the Jordan canonical form. So let's rewrite this transfer function first. This is going to be V0. In the case of distinct eigenvalues, we simply wrote C1 over S plus P1 till C2 over S plus Pn. So for the repeated eigenvalue at S or at P1, this would be C1 over S plus P1 cubed. Let's say 1 1. 1 2 would be P1 squared, and 1 3 would be S plus P1. We have already seen this when we were discussing the partial fraction expansion for repeated ones. Then the rest of the eigenvalues are distinct, so it's simply C2 over S plus P2, Cn over S plus P. If the second eigenvalue was maybe repeated 3 times, instead of this, we could write C2 1 over S plus P2 cube. That's C2 2. And then finally, the last equation for P2. Okay. So in this case, the A matrix is going to be. So for the repeated eigenvalue, we have a repeated eigenvalue at P1, and it's repeating 3 times, so it's going to be minus P1. And so it's going to be a block of size 3 by 3. The diagonal elements will have minus P1, and then we'll have one on the the terms above the mean diagonal, and then zeros. So this is for the first eigenvalue. This. And since rest of the eigenvalues are distinct, it's simply going to be minus P2, minus P3 on the main diagonal till minus P8. So this is the main diagonal. And then we have zeros everywhere else. B vector remains the same, it's simply 1, 1, 1. A is going to be C1 till Cn. And again, D is going to be B0, and it's going to be 0 for strictly proper. Okay. So let's look at an example. If you have any questions, you can just ask me. You can interrupt me anytime. That's fine. So feedback system has a closed loop transfer function of the form by S, where R is 10, S plus 4, upon S plus 1, S plus C. Obtain the Dandel canonical form for the web system. The above system. Okay, so let's rewrite the transfer function. This is simply 10 S plus 4. So the denominator is already expressed in terms of its use. So the first observation is that this is strictly proper. So D is going to be 0. And the next one is that we have distinct eigenvalues or poles at S equals 0, minus 1, minus 3. So this is the simplest case. So the A matrix is going to be, this is a third order system because the denominator polynomial is of third degree. So this is going to be 0, minus 1, minus 3, and then 0 is everywhere else. B is simply 1, 1, 1, and A is 0. And C is going to be C1, C2, C3. So let's compute these coefficients. Alright, so just write this down. The partial fraction expansion of this is simply C1 over S, C2 over S plus 1, plus C3 over S plus 3. So C1 is simply Ys over Rs multiplied by S and evaluated at S equals 0. So this is 40 over 3. So in a similar manner, please calculate C2 and C3 and let me. I'll wait for a few minutes. Let's see. 0 minus 1. I think the first one is already calculated, right? 40 over 3, so it's not 0. Okay, so let's calculate it. C2 is going to be 10, 4 minus 1, minus 1, 3 minus 1. This is going to be 10 times. Yes, okay. And then here, minus 1, minus 3. This is minus 50. And you can also calculate C3 as 10 S plus 4, S plus 1 at S equals minus 3. So if we've already written the answer, it's 5 over 3. Yes. Okay, so you can write the transfer function as 40 over 3, it's 40 over 3 times over s, plus minus 15 over s plus 1, plus 5 over 3, s plus 3. Okay. So let's just look at it a little bit differently. You already have the coefficient, so this is C1, C2, and C3. Okay. So this is the transfer function. You can also write this as 40 over 3 Rs over S minus 15 Rs over S plus 1 plus 5 over 3 Rs over S plus 3. Okay. So in the diagonal form, we considered and this as states of the system. So we have x1 of S, and the S domain, S2 of S, and x3 of S. So let's see. x1 of S is simply Rs over S. And if we want to find the time domain expression, we form the inverse Laplace transform. And this gives S times x1 of S, now passing mix of this is R of S. Or in the state space form, we have U of S. Let's just write this as U of S. So this is x1 dot equals. Okay. Similarly, you have x2 of S equals Rs over S plus 1. We are writing this because you already know that yt is c1 x1 plus c2 x2 plus c3 x3. So x1, x2, and x3 are the states which are multiplied by the coefficient c1, c2, and c3. And we just want to check if we get the same A and B matrices. Let's see the inverse Laplace transform. And what do we get? We get x2 dot plus x2 equals 50. X2 dot is minus x2 plus ut. So this is minus 1 in the A matrix for the eigenvalue of 4 and minus 1. Alright. And then the last state is x3s, which is Rs over S plus 3. We have to inverse Laplace transform. We get x3 dot equals minus 3x3 plus u. So we already have a system, right? x1 dot equals u, x2 dot equals minus x3 plus u of t, x3 dot equals minus 3x3 plus ut. So this translates to the A matrix being 1, 0, minus 1, minus 3, 0 is everywhere else, and B equals 1, 1, 1. So this is what we got, right? So as I said before, the diagonal canonical forms are simply obtained by the transfer functions. So you had the transfer function, this one. You perform the partial fraction expansion. C1, C2, C3 are the elements of the C matrix, and the ratios multiplied by these coefficients give you the state in terms of give you extra. So in terms of x and y. All right. So you already know what y is. That is 40 over 3 minus 50 and 5 over 3. Plus u because it's a strictly proper transfer function. Alright, so I hope this was clear to you. Now let's look at another example. Just a second. Alright. So the transfer function is ys over rs equals s plus 3 s square plus 3s plus 2. So we have to obtain the diagonal canonical form. Diagonal. So the first thing to observe is that it's a strictly proper transfer function, which implies that d is going to be 0. Alright. Now let's look at the roots of the system. These are going to be the roots of the denominator polynomial. So we have to solve s square plus 3s plus 2 equals 0. So the eigenvalues are s equals -1 and -2. So we have s plus 3 over s plus 1, s plus 2. So these are distinct eigenvalues. So it's the simplest case. This is simply going to be c1 over s plus 1 plus c2 over s plus 2. c1 is s plus 3 over s plus 2 evaluated at s equals -1. This is s plus 3 over s plus 1 evaluated at s equals -2. So these are simply 2 and -1. I think we have to use, it's going to be 2 and -1, right? c1 is 2. It's a second order system, so it's a 2 by 2 matrix. A is -1, -2, 0, 0. B is simply 1, 1. C is 2 minus 1 and D is 1, 0. Okay. Let's look at another question. So the transfer function is gs equals s plus 3 equal s cube plus 9s squared plus 24s plus 20. So you have to find the diagonal form. Okay, so the first observation is this is strictly proper. Now let's look at the eigenvalues. So it's s cube plus 9s squared. So let's try s equals -1. It's going to be -1 plus 9 minus 24 plus 20. This is now going to be 0. Try s equals -2. This is going to be -8 plus 36 minus this is 0. Yeah. So let's just divide s equals 2 s2 plus 9 square plus 24s plus 2. Alright, let's see. So this is s square S cube plus 2s square. 7 square plus 24s plus 20. Then let's see the 7s. 7s square plus 40s. It's simply 10s plus 20. This is plus 10. Alright. So we have s square plus 7s plus 10. Now let's see. This is minus 1. With that, we will not solve this. So I suppose minus 2 plus this is 4. So that's it. You can just check if it's correct. No. It's square plus 7 is 10. So this is 14. Alright, so this is 0. Then I think we can just do that this again. This is simply s plus 2s, sorry, square. 5 is plus 10. This is plus 5. Okay. So the denominator can be written as s plus 2, s plus 5, and then it was s plus 2 again. So we have repeated eigenvalues at this. So gs is s plus 3 over s plus 2 squared, s plus 5. So we are going to write the Jordan number form because we have repeated eigenvalues. So Jordan number form. So it's a strictly proper transfer function. So b0 is 0. This is simply c11 over s plus 2 square plus c12 over s plus 2 because we have two repeated eigenvalues at minus 2. This is simply c2 over s plus 5. Okay, so let's calculate for the distinct eigenvalue. So c2 is simply s plus 3 over s plus 2 squared at s equals minus 5. This is, now let's see, 3 minus 5, 3 minus 1 squared. Okay, then we can also find c11 of this, which is s plus 3 over s plus 5 at s equals minus 1. Right? So this is simply 3 minus 1, 2 over 5 minus 1. So this is half. And now we have to find, okay, so minus 2 by 9, 1 by, it's not 1 by 3. Let's see. Which ones? Okay, so we say C is minus 2 by 9 is this. Okay. Let me check. This is single one. So x plus 3 y is plus 5. Okay, let's just check this one. So we can just multiply by S plus 2 square, S plus 5, and then 7,000. So this is, I'm just going to write this directly. And S plus 3 is equal to C11 S plus 5 plus C12 S plus 2 S plus 5 plus C2 S plus 2 plus 5. So we can expand this. This is C11 S plus 5. Let's quickly expand this also. So S square plus 7 S plus 10 is C2 square plus 4S plus 4. Okay, so this is coefficients of S square are going to be C12 plus C2. S is going to be C11 plus 7C12 plus 4C2. Then the constant terms are going to be 5C11 plus 10C12 plus 4C2. Questions? So in comparing the coefficients, of C and values on both sides. We get so C12 plus C2 is going to be 0, implies C12 is going to be minus C2. And I think we already have the value of C2, which is going to be 2 over 9. Alright, so now we have to find C11. So let's see, we can either uh, compare, because it's just one thing. Compare this with this. So let's say 5C11 plus 10C12 plus 4C2 equals 3. So 5C11 equals, let's substitute the values. This is minus 2 only. So we need 5, this is C11. So yeah, this is 1 over 3. So we already have the 3 coefficients. So C is simply going to be 1 over 3, 2 over 9, minus 2 over 9. A is going to be, because we have repeated eigenvalues at minus 2. This is still a third order system. Minus 2, minus 2 and minus 5. This is going to be 1. Then 0 is everywhere else. So this is known as the Jordan block, corresponding to eigenvalue minus 2. For the eigenvalue minus 2. B is simply 1, 1, 1. And D is of course 0. Alright. So let's look at another question. Construct state models. Just a second. Yeah. For the following transfer functions. Right. So By state models, we mean canonical state space ones. So let's look at the first part. The transfer function is 5 over s plus 1 squared, s plus 2. So this is again the case for repeated eigenvalues. This is strictly proper. This is already in factored form, so a is simply minus 1, 2. And for the Jordan block for minus 1, we have formula 0, 0. So we can just, this is the Jordan block. Alright. Then B is, it's a third order system, so 1, 1, 1. It's going to be 0. Now we have to find the proportions for the partial fraction expansion. So g of s, this is c11 over x plus 1 squared plus c2 over s plus 1 plus c, let's just say c2 over s plus 2. So c2 is 5 over s plus 1 squared at s equals minus 2. This is simply 5. And then now we have to find c11 and c13. Let's see. Okay, so let's cross multiply by s plus 1 squared times x plus 2. This is 5 equals c11 times s plus 2 plus c12 times s plus 1, s plus 2, and c2 times s plus 1 squared. So if we put s equals minus 2, we get 5 equals, sorry, this is s equals minus 1. We get c11, which is going to be squared, and the rest of the terms are 0. So we get c11 equals 5. We already know what c2 is. So to find c12, let's see. We differentiate both sides by s. So let's see. Zero equals c11 plus c12 times and s plus 2 plus c12 s plus 1 squared plus 2c2 s plus 1. So let's check once. So 0, c11, we will get it by substituting s equals minus 1. Okay, then we can just expand both sides. Alright, so let's forget about this for a moment and let's just expand. Okay, so this is 5 equals s squared plus s plus 1, so 2s, s plus 2 plus c2, s squared plus 2s plus 1. So this is going to be, let me see, it's going to yeah, okay, let's see the formula here. This is s plus 1. So let's check if we can do it by differentiating this. So x plus s plus 2 and x plus 1. Yeah. It's going to be c12 times x plus 2 plus c12 is plus 1 plus 2c2 is plus 1. Alright, now substitute x equals minus 1 is 0, c11 plus c12, that's it. So this implies c12 equals minus c11. Okay, so C matrix is simply 5 minus 5. No. So we have seen two ways to calculate the coefficients when we have multiple eigenvalues. B0 is 0. It's the coefficient of s to the power. Yeah, you can unmute yourself and ask me the question. That's fine. I'll just go back. A2 is. I don't think we have calculated this correctly. So B0 is the coefficient of s to the power n in the numerator. So if it's this third degree, then B0 will be B0 is cubed, which is a strictly proper transfer function, and the degree of numerator is less than that of the denominator. B0 is inclusive. And then I think we'll have to check A1 is, I guess, correct. I'm not sure we have written A1, A2, and A0. Uh, Dhana Sekhar Ji, you can just ask me the question. Can you unmute yourself? Also write a question in the chat box. That's fine. I'll wait for a minute if you have any questions. All right, so I'll move on. If you still have a question regarding this, you can just write it in the chat box. Or you can unmute yourself and ask me. That's what's fine. So let's look at the next part. G of S equals S cube plus 8S squared plus 17S plus 8. And then we have S plus 1, S plus 2, S plus 3. Okay, so what do you observe? First of all, it's a proper transfer function. Why? Because first of all, these are the coefficients B0, B1, B2, B3, and B0 is not equal to 0. It's a proper transfer function. D is not going to be 0 in this case. So we have distinct eigenvalues. Of course. Okay. So if it's distinct eigenvalues, A matrix is going to be simply -1, -2, -3, zeros everywhere else. Then B is simply 1, 1, 1. And recall that in the case of a proper transfer function, B is equals V0. Therefore, we are 1. Okay. Now we have to find the coefficients and therefore the vector C. So G of S is simply going to be B0 plus C1 over S plus 1, C2 over S plus 2 plus C3 over S plus 3. This is S cube plus S square plus 17S plus 8 over S plus 1, S plus 2, S plus 3. Okay, so C1 is going to be, so you can observe that if we cross multiply by this S plus 1, S plus 2, S plus 3 and substitute in steps S equals -2, S equals -3 and S equals -2 means then this would be B0 S plus 1, S plus 2, S plus 3. So you can observe that this B0 does not have any effect on the calculation of C1, C2 and C3. Alright, so C1 is therefore simply x cube plus 8s squared plus 17s plus 8 over s plus 2, s plus 3 evaluated at s equals -1. This is going to be s plus 1, s plus 3, and finally we have C3. So you can please calculate and let me know the answers. S cube plus 8s squared. Okay, so what are C1, C2 and C3? Okay, so you can check this in the language of output. This is -1. So I see vector is simply -1 to 1. It's -1. And I think we're not getting them in the correct order. So okay, so it's 2 to 1 and then it's -1 to 1. You can just check this. You have to write it in the correct order because the output one is going to be -1 to 1 multiplied by the sector. It's 1 x. Right. So let's move on to the next question. Student forces. That is in the US, and that is 50 1 plus S05 S 1 plus S02 1 plus S50. And we have to obtain the diagonal. So you can see that this is first of all strictly proper. And we have distinct diagonals. Okay. Okay, so let's first rewrite this. This is going to be 50 S plus 5 plus 5. And then we have 50 into 2 S plus 2 S plus 50. This is equal to S plus 5 S plus 2 S plus 50 means 50 over 5. So I think this is correct. Okay. It is simply 1000 S plus 5 S plus 2 S plus 50. Okay. And we have to write it in the form C1 plus, okay, let's see, C2 over S plus 2 plus C3 over S plus 50. These are the distinct eigenvalues and let's write it here. That is equal to 0, -2 and -50. So A is simply 0, -2, -50. Then B is 1, 1, 1. And D is going to be 0. Okay. So C1 is, now let's see, 1000 into 5 over 50. Let's give us the difference. Plus 50. And check. There are 3 states. I'm not sure if it's the answer to this question. 5 and 1.16. Maybe it's the last one. Okay, you also had the question which you're referring to because it's a little bit unclear. Alright, so C2 is 1000 is plus 5, Sn is plus 50, evaluated at x equals -2. This is 3 minus 2 and 40 versus 3 by helpless. 3 into 10 to the power 3. 1 to its, you can just simplify this. And similarly, C3 is 1000 times this plus 5. And then S is plus 2. Value that S equals minus 50. So you can write the simplified expression for this. C is simply C1, C2, C3. So you just now you can also choose eigenvalues in a different order. If you choose eigenvalues in different order, for example, let's say S equals minus 2, 0, minus 50. Then the A vector would be minus 2, 0, minus 5. B would remain the same. D would remain the same. And C, I think we have coefficients using the notation from here. It's going to be C2, C1, and C3. So just be clear of the order of the states which you are using and then calculate or write these vectors. Alright, so this is clear. Let's move on to the next question. Now instead of transfer functions, we will have differential equations. So construct state labels. Construct canonical. Use these models. This can be done in terms of CCF, mostly for diagonal forms. We will write it in diagonal form. For the following differential equations. So the first one is total derivative of 5 is nothing of derivative plus 11 by dot with 6y equals 3. So we saw in the last week's limit session that we can convert it into S domain by inverse Laplace transform. So this is, sorry, just Laplace transform. And assuming zero initial conditions. So in this case, this is simply by S times S cube plus 6s square plus 11s plus 6 equals rho of S. The transfer function is rho is 1 plus S cube plus 6s square plus 11s plus 6. So it's a strictly proper transfer function. And now let's look at the eigenvalue on the poles. So this already implies that D is 0. So let's see what are the roots of the denominator polynomial. So S equals minus 1. If you substitute S equals minus 1, we get minus 1. So this is S squared. Plus 6 minus 11 plus 6 which is 0. So let's look for other roots. And then plus 2 plus 6 squared. So everything is plus 6. Alright, let's see. It's 1 0 0. Alright. So S cubed plus S squared. 5 squared plus 11s plus 6 is 5 plus 6. Okay, so We can also simplify s square plus 5s plus x. So I think it's going to be, if you write s equals minus 2, we get minus 4 plus 6 minus 10 plus 6. Okay, so the rules are, I'm just going to write this down. 1 over s plus 1 is plus 2. Now it's going to be s plus 3. You can just check this. So we have distinct eigenvalues. This means A is simply minus 1, minus 2, minus 3. We already know what B is going to be. And now we need to find C1, C2, C3. So I'm just going to write this down directly. C1 is 1 over s plus 2, s plus 3. Value of that s equals minus 1. So this is plus 2. This is half. I think you wrote 1, 0, 0. I don't think that's correct. We should check this. C2 is 1 over s plus 1, s plus 3, what is equals minus 2. This is going to be simply minus 2. Yeah. C3 is 1 over s plus 1, s plus 2, that is equals minus 3. It's going to be minus half. Yes. Okay, so it's plus. So C is half minus 1 half. This is C. Alright. So let's consider another differential equation. That's triple dot plus 3y double dot plus 2y dot equals u dot plus u. So in the Laplace transform, assuming zero initial conditions, we get, let's see, minus over us is going to be s plus 1, s cube plus 3 square plus 2s. Okay, so this is strictly proper. Which implies d is going to be c. This can also be written as s times s square plus 3s plus 2. And this is going to be s plus 1 s, and then here s plus 1 s plus 2. So you can see that here pole zero cancellation. Alright. So in this case, if we write a equals 0 minus 1 minus 2, this won't be correct because we actually have a second degree in the denominator column. So let's see. GS is C1 over S plus C2 over S plus 1. So A is going to be actually just 0 minus 1 in the second order system. B is going to be 1 1. And then C1 and C2 are going to be 1 over, sorry, this is minus 2. This is the number is equals to C1 is half and C2 becomes minus 1 by 2. You see this half minus half. Now let's look at another differential equation. This is the triple dot plus 6y double dot plus 11y dot plus 6y equals u triple dot plus 8u dot double dot plus 17u dot plus 8u. So again, we have to find the diagonal form. If you can observe that the degree of the denominator polynomial is going to be 3. And if we take the Laplace transform for u, we also have s2 here. So this would be the case of b0 equals 1 or for proper transfer function. Right, so let's move the Laplace transform. Again, assuming zero initial conditions, we have pi s over u of s is cubed plus 11 square plus 17s plus 8 plus s cubed plus 6s square plus 11s plus 6. So I think the denominator is the same one as this. 6, 1, 6, 11, and 6. Yeah. This is simply s cubed plus 8s square upon s plus 1, s plus 2, s plus 3. Okay. So a is simply going to be minus 1, minus 2, minus 3. B is going to be 1, 1, 1. D is 0. And C1 is. So we have to write this G of S. C1 over S plus 1 plus C2 over S plus 2 plus C3 over S plus 3. So in C1, it's S cube plus 8S square C2 plus 17S plus 8 over S plus 2 S plus 3. Sorry, D is not going to be 0. D is 1. So you can just calculate it, let me know what C1 is. So let's see. Minus 1 plus 8 minus 11 plus 8 over 2. So this is minus 1. Then C2 is S cube plus 8S square. I think it's minus 1 and we only have 3 states, so it's not sure to be written. We only have 3 states, so I don't have, I think 1, 2, we have 6 states. I'm not sure how many it is. You can also unmute yourself if you want to say something. because this C vector is incorrect. So D is plus 8, the word is plus 1 is plus C. When looking at S equals minus 2. It's plus 2 minus plus 1. Okay, so what are C2 and C3? Can you calculate these in a minute? Okay, so let's see. This is going to be minus 8 minus 4 plus 8. So it will be simply 2. This is going to be so you can check and this is 1. So C is simply minus 1, 2, and 1. Okay, so that's it. This was the last question. If you have any doubts regarding the questions discussed in this tutorial session or in the assignment, you can ask me. If not, you can leave. Alright, so if there are no questions, let's end this meeting. Thank you, and we'll meet again in the next tutorial session.